Hi, I am Subhanil Bagchi. Welcome to our presentation for the work Learning a Meta-Ensemble Technique for Skin Lesion Classification and Novel Class Detection, undertaken with my colleague Anurag Banerjee under the supervision of Dr. Deepti R. Bathula. The International Skin Imaging Collaboration ISIC has developed the ISIC Archive, a repository of dermoscopic images for clinical training as well as supporting research towards automated analysis. The goal of ISIC 2019 challenge was to classify the lesion images among 9 different diagnostic categories, where 8 are labeled and the ninth is unknown. We were motivated by existing literature where ensemble techniques yield good results. To incorporate novel class detection, the second level of our hierarchical model simulates unknown classes for training. The images in the dataset have been acquired from multiple sources. The 25,331 images are not uniformly distributed across the classes. This imbalance may be observed by contrasting the sample space for class NV against classes AK, SCC, VA, SC, and DF. The unknown class images are presented to our system at the test time. As you can see, the raw images as part of the dataset shown in the top grid has huge variation in illumination. So to mitigate this, we have applied the shades of gray algorithm to obtain channel normalized images. This algorithm achieves color constancy by generalizing the gray world hypothesis, which states that average scene reflectance is achromatic, and the max RGB algorithm, which states that reflectance across all three color channels is equal. We may observe the results of this in the bottom grid. The first level of our hierarchical model is the stacking module. For base learners, we have used pre-trained networks, namely one configuration of the EfficientNet B2, two configurations of the EfficientNet B5, and one configuration of the DenseNet 161. We decided these models based on their performance on the ImageNet dataset. Our meta-learner level consists of a 3-layer fully connected neural network. Standard data augmentation techniques such as rotation, translation, flips, and cropping were applied dynamically at runtime for each epoch. Models across each level were trained using weighted cross-entropy loss to mitigate class imbalance. We use the following input configurations for the base learners. For each base learner, the given images are first resized to 512 x 512. Then, in accordance to the crop ratio column, random crops were generated at runtime, which were resized as per the image dimension column. Let's look at the training process for the stacking module. First, we partition the given image dataset for stratify 5-fold cross-validation as shown in the figure. For a particular fold, all of the base learners are trained independently to produce individual classification probability space. The holdout validation set is further partitioned for stratified 2 folds to train the meta-learners. For each inner fold, the images are transferred to the output probability space of base learners, where model predictions are concatenated to generate a new feature. The meta-learner is trained on this feature space to dissipate the base learner's bias. The process described was one of the outer 5 folds with one inner fold. It is repeated for all the inner folds across all the outer folds. Further, upon visualizing some validation set embeddings using TSNE across both the average of base learners and stacking module, the stacking module seems to show better class separability as given on the right image. For another validation set, the separability learned by the stacking module is still better than the simple averaging. The second level of our hierarchical model is a collection of one versus rest classifiers, which we call the CSKSU module collection. Each classifier of this collection treats one of the 8 classes as known and the rest as unknown. To train each such binary classifier consisting of pre-trained ResNet 18, a fully connected network, the data is split into known set and simulated unknown set. Data augmentation similar to stacking module is applied. Training utilizes both weighted cross entropy and triplet loss. To generate the splits, first we divide each class into equal halves A and B. For each class treated as known, say C1, first C1A forms the known class set. 6 of the remaining classes form the simulated unknown class. C1B and the B half of the remaining 7th class form the validation set. 7 such combinations are possible by leaving a simulated unknown class out for validation strategy. This is similarly repeated with B halves forming knowns and unknown set, with A half forming the validation set. Thus, we have 14 such fold sets as shown in the figure. We use each fold set to independently train separate models as shown. The outputs of each such model are binary classification probabilities. Therefore, for each known class, we have 14 such models. The final classification probabilities for a CSKSU model are obtained by averaging the results of these 14 models. Using the unknown class probabilities for the validation set, we perform a grid search over the thresholds to obtain the balanced accuracies. The threshold for the particular CSKSU module for a known class is then empirically decided based on the balanced accuracies. Our choice of cross entropy is based on the class imbalance problem. In weighted cross entropy, the weight coefficient associated with the classes decide the penalization for incorrect instance classification. The triplet loss is computed in the embedding space. It aims at increasing the interclass distances while reducing the intra-class distances. Its objective was to ensure a gap of margin between the knowns and simulated unknowns. Let us now look at the testing process for the complete model. The test image is passed to the stacking modules of all the outer 5 folds, each consisting of 2 inner folds. This gives us the per class classification probabilities. The probabilities of these 10 modules are then averaged, and the argmax over the probability vector gives the class predicted by the stacking module. As the next step, the CSKSU module for this particular class is then used to make a conclusive call about the instance. If the CSKSU module predicts it to be unknown, we declare the image to be a member of some novel class. Our methods have been evaluated on the ISIC 2019 Life Leaderboard. We have compared our results with some of the other submissions on the Life Leaderboard itself, as shown in Table 1. It can be seen that the stacking module has 0.025 better balanced multi-class accuracy score than simple averaging of the base learner's output. It can also be seen that our CSKSU module increased the unknown class AUC while introducing a trade-off in the overall BMA score. Table 2 shows the per class AUC for each of our methods. These are the ROC plots for each of our methods as discussed before and can be found on the ISIC 2019 Life Leaderboard. To summarize, we have proposed a 2-level model where we observed that stacking outperforms simple averaging of base learners. CSKSU modules give promising results but may not scale well with increase in number of classes. The trade-off between increase in AUC for unknown class and decrease in overall BMA score highlights the difficulty of the challenge. We further believe that introducing extra data may improve the performance. Thank you.